Welcome back to the module 3 where we are discussing nonlinear optical effects. In the last lecture we have discussed high harmony generation process, and so far we have discussed a single atom response. We will recapitulate what we discussed. We had a molecule or atom, an intense laser field is propagating along this direction. So, I have considered one atom, and then due to tunnel ionization, due to this intense laser beam, I have removed an electron from this atom. This electron is now free, and because the electric field is changing along this direction in every optical half cycle, this electron will face a force due to the electric field, and it will go away from the cation and then come back, and there is a possibility that this electron will recombine. If this electron is recombining, then it can produce high harmonic emission. So, that is the single electron, atomic response or single molecular response we have discussed. But we know that for any nonlinear process, phase matching is an important concept. So, high harmonic generation will have the same issue, and we should understand the phase matching condition which can control the conversion efficiency. Starting the HIG process in a single atom response model basically provides the predicted shape of the harmonic spectrum. So, what we have seen that single atom response, that 3-step model can provide us to explain why the cutoffs are like this. So, generally this is the nature of the spectrum we see. We see a gradual drop for the lower harmonics, 3rd, 5th or so on, and then there is a plateau regime for the high harmonics, and then suddenly there will be a cutoff. And this cutoff we have explained with the help of 3-step model. We have got the analytical expression for this cutoff. That cutoff we have expressed as h nu max, that is going to be IP plus 3.17 UP, and we have seen why we get this 3.17 factor. This is the maximum cutoff energy, and in order to increase the cutoff further to the higher photon energy, what we need to do, we have to change UP, that is point normative energy, which will depend on the driving laser wavelength as well as the intensity. But then question is, phase matching is an important concept, and what does it mean by phase matching? Phase matching is something which we have explained already. Let's look at this second harmonic generation process. We have a fundamental beam propagating through the medium, and we said that due to propagation of this fundamental beam, we create polarization in the medium. Polarization is nothing but oscillatory dipole. So, we consider two dipole which we have created at the beginning of the medium and in the end of the medium when the fundamental beam is propagating. So, each dipole will produce its own emitted field, and that is the SIG field. Now, this dipole will create this SIG field, and this dipole will create this SIG field. If these SIG fields are in phase, then we call it phase matching is achieved, and we get the higher conversion efficiency. We see the new beam, new light generation. On the other hand, if these dipoles are creating fields which are not in phase anymore, they are out of phase, then even we have this nonlinearity present in the medium, we will not see any input, any conversion of the frequency. So, phase matching is an important issue, and we have to follow certain procedure to bring them in phase to improve the conversion efficiency. To obtain strong harmonic emission, which means that we have to increase the efficiency of the frequency up conversion process in HIG process, phase matching condition also need to be considered. A useful introduction to phase matching conditions is already given in our previous lectures with an example of the second harmonic generation, which we have also shown here. This highlights that to produce optical harmonics efficiently, the process must be phase matched. That is, the fundamental beam or induced polarization and harmonic beam must be brought in phase throughout the nonlinear medium. Furthermore, we have seen that intensity of the harmonic emission is given by this expression I LT. L is the thickness, which is nothing but mu naught square omega naught to the power 4. This expression we have already obtained in our previous lectures. B Z T L square. Then there is a cardinal sine function we have seen, that depends on delta K L by 2, and this delta K is the phase mismatch, which is nothing but K naught minus Kp. K naught is the outgoing beam. So basically we remind that when we consider input beam, this is the input beam. We have expressed input beam as A1t e to the power I omega 1t minus K1z. This has induced a polarization. This polarization will depend on how they are related. They are related by the Taylor series expansion. Let's say if it is second harmonic generation, then we can write down epsilon naught chi second order e to the power input beam square, that we have seen if this is second harmonic generation. If it is higher order harmonic generation, then this is going to be n. This will be n. And this polarization was expressed with the help of Bt, that is exactly written here, Bt e to the power I. Then we said that we will write down this. If it is second order polarization, then it's going to be 2 omega 1 minus 2 K1z if it is second order, and so 2K1 is actually Kp, polarization wave vector. And then due to this polarization, I have created new emitted beam, that is E emitted, and that is related by the nonlinear optical equation we have written previously. And that can be written as A emitted beam, then e to the power I omega naught t minus K naught z. So this K naught is the wave vector of the emitted beam and Kp is the wave vector of the nonlinear polarization. So these are the expression we have seen, and L is the distance traveled in the medium. This equation shows that harmonic intensity varies as the cardinal sine functions. This cardinal square sine function, this function will control the efficiency. And we know that this cardinal sine function, if we plot this cardinal sine function, then we see that there is a sharp drop, which means that little bit of phase mismatch will bring the efficiency down to 0. So this is at a 0. This is if we plot delta K L by 2, then we get cardinal sine functions like this. Very sharply it drops down. Its maximum when delta K equals 0. This is maximum, and it drops down very quickly when there is a phase mismatch. So this delta K issue, bringing them in phase, we have to consider for the HHG process as well. The phase mismatch delta K, as mentioned before, for the qth harmonics, let's say, for the HHG process, which can be written as delta K Q, qth harmonics, equals K naught Q minus Kp, which is nothing but QK1. K1 is the input beam. We have shown that it is related like that way because input beam we will consider as A1 e to the power I omega 1t minus K1z. That was the input beam. and the polarization will be then written as if it is qth harmonics, then it's going to be e to the power I q omega 1t minus q k1z. This was the expression. So this is the wave vector of the polarization. So we have to understand that previously we considered the refractive index of the birefringent crystal for the second harmonic generation or third harmonic generation. But here we are not using any crystal, we are using partially ionized gas medium. The gas medium which we are using, they are partially ionized, which means that we have neutral molecules, electrons, cations, all are put together. Q is the harmonic order here, and K naught Q is the wave vector of the qth harmonic. K1 is the wave vector of the fundamental beam, and for partially ionized gas medium, the refractive index can be written as this: K equals 2 pi by lambda n, and n, refractive index of the partially gas medium, is given by this, where this capital P is the pressure, this P here we express in this equation, in this refractive index expression, P is the pressure of the gas medium, and eta is the ionization fraction, and in atmospheric it is number density at 1 atmosphere. It is the number density in 1 atmospheric pressure, and n lambda is the refractive index of neutral atoms. So what we get is that an expression we get, we can try to understand the meaning of this expression. There are 4 terms here, 1, 2, 3 and 4. There are 4 terms here. The first term contribute to the vacuum dispersion. We know that in vacuum when it propagates, we know that it is going to be 2 pi by lambda. That's why the first term is the vacuum propagation. The contribution coming from neutral gas dispersion is coming from this term, second term, neutral gas dispersion. So 1 minus eta, eta is the ionization fraction, which means that 1 minus eta is suggesting that the neutral fraction of molecules which we have in the gas medium. The third term is the plasma dispersion. Plasma is nothing but a combination of, it's a fourth state of medium. It's combination of electron, ions, neutrals, everything together. That's called plasma. So plasma dispersion is then charged gaseous species, and that medium will have a different dispersion. That dispersion depends on the pressure, then ionization fraction, how much molecules has been ionized, and then characteristic radius of electron, and then lambda square by 2 pi. These are the coming from directly from the plasma characteristics of the medium. And the last one is the nonlinear refractive index, which is, that's why we have N2 term, which depends on intensity. So intensity is going to also contribute to the phase matching. So for partially ionized gas medium confined inside a waveguide, additional dispersion term due to waveguide is also included, and the magnitude of the propagation vector can be written as we have to include this term as well, plus mu m n square lambda divided by 4 pi a square. In general, HHG process can be HHG frequency conversion can be obtained in a gas medium, in a very short gas medium, in a very long gas medium, or in an waveguide also. So waveguide has a break here, so we are injecting gas molecules through this waveguide. So if we have waveguide, then we have to include the waveguide dispersion term as well in the medium. So that goes in. If we don't use waveguide, then we do not need this dispersion contribution. We can avoid that. So here, what does it mean by this waveguide contribution? A here is the inner radius of the waveguide, and mu mn is the characteristics of the waveguide mode. For a gaseous medium, this equation is sufficient. However, we have to consider waveguide contribution as well if we produce HHG in the waveguide. So the phase mismatch, which we can write like this way by this expression, and this expression gives us the phase mismatch between the emitted beam, HHG beam, and HHG polarization. That is going to control the phase matching. The phase mismatch can be given by this, which has this expression here. Waveguide contribution we have included. If we are not using waveguide, then we can remove this contribution. The phase matching of HHG can be achieved. That is, we can have a condition delta Q equals 0 by balancing various parameters given in this equation. In this equation, there are parameters which are looks positive, looks negative, and looks negative. So we can balance them positive, negative, such a way that in the end this delta K can be 0. And the parameters which we can control in this phase matching process is going to be pressure. Of course, pressure can be varied. Then ionization fraction, how many molecules we can ionize, that can be varied. And in the waveguide, we can also vary the mode quality of the waveguide. That also we can vary. Let us now take a closer look at these factors which can contribute to the phase mismatch, because the harmonic yield is severely affected by phase mismatch. The first term in this equation arises due to phase mismatch caused by neutral gas dispersion. So this part is neutral gas dispersion. And this one is plasma dispersion. These are the two important contributions in the HHG process. And we'll see that by balancing these two contributions, we'll be able to achieve this delta K equals 0. This neutral gas dispersion depends on pressure, difference of the refractive indices, this one, at the fundamental and harmonic wavelength, and ionization fraction. So there are three controlling factors I have for the neutral gas dispersion. P, pressure, 1 minus eta, that is the amount of gas molecules will be ionized, and the difference between these two, at what wavelength we are creating the HHG. Ionization fraction, which determines the ratio of neutral atoms and ionized atoms, solely depends on the intensity of the fundamental laser beam. So how much intensity we use, that will control eta. But at the same time, the neutral gas dispersion is negative. So although it may appear to be positive, but it is actually a negative contribution. Negative contribution is because the delta n, what we have written here, lambda 1 by q minus n lambda 1, this is negative always. Why? Is because the refractive index in the X-ray regime is less than 1. So this value is always less than 1 and this value is always greater than 1. This is the driving field. So this refractive index is, let's say, 800 nanometer refractive index, and this refractive index is going to be X-ray refractive index. And in general, the medium 800 nanometer refractive index is going to be always greater than 1, and these are refractive index, and X-ray refractive index is always going to be less than 1. That's an important, and there is an important consequences for this, for the X-ray optics. We will not discuss those X-ray optics immediately, but what we see that this term is actually negative term, this refractive index difference in the neutral plasma dispersion, and because it's negative, the finally neutral gas dispersion becomes negative. So this neutral gas dispersion, instead of positive, this term becomes negative. The second term, which is plasma dispersion, on the other hand, is positive because Q is greater than 1 by Q. So this is negative. So this negative is contributing to this negative. So finally this is becoming a positive contribution. When an intense laser beam interacts with a gas medium, free electrons are emitted. These free electrons cause plasma dispersion. As the contribution from the phase mismatch due to neutral gas dispersion is negative, and due to plasma dispersion is positive, the total phase mismatch can be reduced by varying the laser intensity to adjust the ionization fraction. Considering gas jet, for the phase mismatch condition, for matching condition, when the phase mismatch due to neutral gas dispersion is fully compensated by that due to plasma dispersion. So basically what happens, I want to make this to be 0, and the only way I can make this to be 0 is balancing this positive and negative contribution to the phase mismatch, and that will control the finally the conditions which will fulfill the phase matching or the conversion efficiency in the HIG process. With this, we have come to the end of this module. In this module, we have discussed different nonlinear processes. We started with linear versus nonlinear polarizations, how they are affecting, how nonlinear polarizations are creating new input beam, and we have seen the phase matching is also an important concept in nonlinear frequency conversion processes. So if the phase matching is not achieved, then we may not be able to get the efficient conversion for that particular conversion or nonlinear conversion. We have discussed polarization gating, we have discussed transient grating spectroscopy, we have discussed some frequency generation, difference frequency generation, and in the end we have discussed high harmonic generation, which is a source, which provides a source for ultra fast X-ray pulses. With this, we'll end this talk, and we'll meet again for the next module.